So in previous lecture, we discussed why we need a synchronization mechanism in implementing multi-threaded program. And because multi-threaded program basically assume that thread scheduler of an operating system, or sometimes it is implemented by user level library. Anyway, the thread scheduler can execute the thread arbitrarily order. Arbitrary order here means that basically by default, there is no ordering constraint enforced across thread. I mean, within a thread, there is an ordering among the instruction, right? There is a sequential order of the instruction. Those ordering is basically kept. That is how each thread get executed. However, among the two threads that concurrently learning, we don't have any ordering if we do not put some mechanism to enforce or constrain possible scenario of their intermixed or interleaved execution. So we need to have a mechanism for programming intended ordering or intended way threads can interact. Otherwise, we cannot enforce atomicity of a critical sections. And if that is not possible, we cannot write correct program. So synchronization is one of the essential aspects in multi-threaded program. And I told you that there can be a various way for achieving that, and various paradigm exist. And some paradigm is better for some application, and some paradigm is better for the other. And I told you that there are tons of different approaches. It's similar to the programming language and programming paradigm. We have a very different programming paradigm, and depending on a situation, some paradigms fit better to some situation and some paradigms do not. And they have all different purpose, and there are all different reasons they exist. In a similar manner, we have different multi-threaded programming paradigms. And what we are learning is one of the very popular and widely used ones. And I told you that this way of the programming is often referred to p-thread programming. Yeah. And in implementing p-thread library, yeah, mutex or log is one of the fundamental synchronization mechanism. And when I explain it about some real-world analogy, another word example that share the same intuition as a log in previous lecture. And here, let's talk more technically about a log. I think I already did a pretty detailed explanation on the log, but I'm repeating it. So log is a mechanism that enforces series of an instruction to be executed atomically. Atomically means that either execution is done, never done, or done. But there is no intermediate state about allowed it. So even though there is some non-deterministic thread scheduling interrupt happen, log mechanism is to guarantee that series of instructions to be executed atomically. And log is implemented as a special variable. They are actually a variable. I think if you already checked the p-thread tutorial video, then you already saw how to implement, how to use a p-thread mutex. P-thread mutex is exactly one of the implementation of a locking mechanism. And in order to use a p-thread mutex, you saw that you need to instantiate, you need to declare mutex variable, mutex whose type is a mutex t, right? So it's a kind of a special variable, but the instruction that manipulate this lock variable is different. It should not be ordinary read and write, but lock and unlock operation must be used. Lock and unlock operation must be used. So lock can be contained or can be held by at most one thread at a time. So Lock can be held by no thread. That's good. In that case, we see that the resource that is represented by the lock is free or available. Free or available. So lock is there. So anyone can acquire that and hold that. But if lock is held, it should belongs to only one thread. So to provide mutual exclusion with it. So that it's a special. So so you can think, so here, so let me elaborate it on a little more. So lock variable, since it's a variable, can contain a value, and this value can be either available or acquired, available or non-available. Non-available means that somebody already hold this rock, so the resources resources already acquired it. So we can think the lock variable, so lock n, and it can have a variable available. I represent available as 0 and acquire as 1. So initially, this one is define it as a 0 available, and then what? I told you that thread 1 and thread 2 can check the value of m, but it should not track the value by read operation. Yeah, but it always needs to check the value by log operation. And log operation sometimes referred to acquisition, because this is an attempt to acquire log if it is available. If it is available. So thread number 1 can apply log operation on m. And the behavior of this log operation is that it first checks whether m value is available or not. And in this case, this is available, right? In this case, this is available. So what will happen? It just moving on. This operation just executed successfully, and control flow goes to the next instruction. And at the same time, log value will be updated as a non-available or acquired. And it is augmented as that the owner, the one who acquired this log at this moment, is thread number 1. This information is also attached. And all these steps happen atomically. That's an important point. All these steps happen atomically. So this behavior cannot be implemented by read and write operation, the read and write operation that we ordinarily know. Why? Because ordinary instructions, or if it is ordinary case, we have no guarantee that series of instructions are guaranteed to be atomically executed. But log operation is designed intentionally to be execute all those steps in atomic manner, so that we can use this instruction to provide larger degree of a mutual exclusion. I mean, log operation, this operation itself provide a functionality of a mutual exclusion, because it guarantees series of different steps happening at the same time atomically. So by utilizing this log operation, we extend the scope of the mutual exclusion to a block of the code that is guarded by this log operation. Okay. And moving on. So what happened? So suppose that thread number 1 is executing this some instruction after this log operation, and thread number 2 is also acquiring log m. Then what will happen? It checks the value of the m, and in this case, log variable is not available. It's already acquired. Then what happened? Then it should be blocked. I mean, this operation will be blocked. So control cannot move on to the next step. Why? Control can be moved on to the next step only when this thread, the caller thread, holds the log. and which cannot be satisfied at this moment. So it will be temporarily blocked until when? Until it holds the lock and become its owner. So it will be just a block at this moment. Even if these two operations happen, I mean, even if this lock operation and this lock operation happen right after each other, the second one will be blocked. Why? Because log operation, even if it were 0, if this log operation happened earlier, then what? Atomically, it checks the value of the 0 and updates 1. So in all cases, it is guaranteed that the thread who tracks lock variable being available is at most 1. At most one thread can track lock variable being available. So it will be blocked, and afterward, eventually thread number 1 needs to call on unlock n. Then what? Lock variable turns to 0 and become available. And at this moment, thread number 2 now checks n being 0 and turning it into a 1 and become its owner. And now thread number 2 is holding lock n so that it can successfully move on to the next instruction. Suppose that before unlock, and here lock 2 is, suppose that lock 2 is blocking and waiting for acquired holding lock n. At this moment, what about thread number 3? New one comes in and executes the lock operation on n. Then what will happen? Thread number 3 will also gets blocked because lock is not available. And thread number 1 is releasing lock n here. Then what? And oops. Who will get locked here? Basically, there is no ordering. So as the lock become available again, one of the thread that is waiting for holding lock n will hold the lock and proceed execution. There is no ordering among these waiting threads. It largely depending on the thread library implementation and also some runtime situation of the program that decide who will take the lock in next turn. But basically, we have no rule for deciding who will take the lock next among the waiting thread. 이거 이해돼요? 이것도 규칙이 없어요. 아무나 해도 되게끔 그냥 정해져 있습니다. So suppose that thread number 3 happened to be, it was thread number 3 who will take the lock. In such a case, thread number 2 remains blocked, and thread 3 become an owner of the lock and proceed its execution. Or thread number 2 get a lock and proceed execution, whereas thread number 3 remains blocked and waiting for lock to be released and get the lock, hold the lock in next turn. That's how it goes. Any questions so far? No? Okay, I'm moving on. Okay. So if such lock mechanisms are given, we can nicely use them and we can provide atomicity guarantee of the block of the code through utilizing lock operation. But how can we, but before discussing about how we utilize the lock and implement concurrent algorithm, before moving on there, let's look a little more about how to implement log operation itself. How to implement log operation. Here I brought a piece of the code that become a kind of a naive approach for implementing locking. So how do you implement the lock? We can think in this way. Suppose that we first define a lock variable in this way. Okay, so we here put a flag, and flag can be either 0 or 1. This become a lock variable, and then yeah, we have a API for initializing a mutex. It make a lock 0 to represent it being available. And then what? We have a lock operation and unlock operation. Unlock operation is easy, so let's first check that. What? It just turn the flag into a 0 again. Then it naturally represent log is available now. And tricky part is log operation. So how do you write the behavior of the, how do you specify the behavior of the log operation? In this way, it first checks the mutex value being, flag value of a mutex being 1 or not. And if it is a 1, it means it's not available. So then what? Just spinning on here until this condition to be satisfied, right? And then what? Whenever the flag becomes 0, then it escapes from this looping and turning the flag 1 to declare that this log is now held by the running thread, the thread who execute this code. Make sense? Yeah, it kind of, it do provide a essence of locking behavior, right? I mean, this is represent the blocking, and this represent, yeah, marking of the flag into unavailable or occupied. So it kind of, this can, these codes represent the basic behavior of the log operation and unlog operation, but I think you already see this incorrect or something is not perfect for this code, right? Why? What's the problem here? Here the problem is that what? Two different threads can track flag being 0 at the same time and passing on to the line number 11 at the same time. Do you see that chance? For example, do I have an animation here? No, I did. So for example, log is suppose that log flag is 0 and thread number 1, thread number 2, both of them check this variable at line number 9. In this case, both of them check the flag is being 0, and here also both of them see that flag being 0. And then what? After executing this one, what if context switch happens to thread number 2? And thread number 2 also check the flag being 0, and what it does is update the flag by 1 and line number 11. And then at some point, context switching happens again, and control comes back to the thread number 1, and it also checked that, okay, flag was 0, so it already passed it on this loop condition, and then it move on to execute the line number 11 and make the flag 1. Then what? Thread number 2 and thread number 1 and thread number 2, both of them can enter into the critical section at the same time, all right? Because it make a 2 thread being owner of the log at the same time. So this is a wrong implementation. If you really write the code in this way and execute it a multiple time on your machine, then you can easily make the race condition and see this type of thing happens. Do you see? Okay. And then, so what's the problem here? Checking and setting of the flag. Checking and setting of the flag must be happen atomically, but it wasn't happen atomically. So interrupt happen in between, and race condition makes mutual exclusion impossible with this code. So this is not a correct implementation. Then what kind of approach we can take? There are 3. First approach is that instead of doing this kind of stuff, what it actually does is that at log operation, it just disable interrupt. This is a kind of a, and then unlock, it just enable the interrupt back. Do you see this is a, what do you think? Do you think can we achieve the expected behavior of a log and unlock operation by implementing them in this way? Truth is that it does provide the correct behavior, because by disabling the interrupt, it removes the fundamental possibility of having context switching afterward, right? If timer interrupt doesn't happen in any cases, then no context switching happen, because yeah, context switching, especially the preemptive context switching, relies on timer interrupt mechanism. So this will make the code followed by this operation to be executed atomically. So this is a correct implementation. But what's the problem here? There are several problems here. First one is that the foremost reason, so this is one possible implementation of the log operation, but it's not really widely used anymore, because most of all, this is really dangerous. This is a really dangerous implementation. Dangerous in the sense that, what if we execute the log operation, and then at some point, for the region with that we could not consider correctly, properly, program fall into an infinite loop, or program fall into an operation which requires some devices to raise some interrupt. Yeah, if such thing happens, then the whole system becomes unavailable, or whole system went wrong by such mistake, and there will be no mechanism to alternate the execution of the alternate the escape those blocking, because the usual mechanism for escaping some program execution is interrupt. But if interrupt is totally disabled, then system went to be blocked indefinitely. Something went wrong, and something went, there is always a possibility for program to be crashed for different reasons, and there is always a possibility for a program to have a bug. So this approach, this operation, disabling the interrupt, is so risky if the following region of the code is lengthy and it contains some non-trivial logic. So what if after disabling the interrupt, what it executes is only a few instructions that is very clear, then it is all right. Then it is all right. But if it is not, then it is very critical and risky. And especially disabling and enabling of the interrupt usually is a job for the operating system. It shouldn't be a job for the application program. But if a log operation is implemented this way, application program intentionally call on log operation to disable interrupt and exploit the system. So we cannot make such a chance to the application program. So this is not a proper way for providing log operation to the user level program. Makes sense? But I think I already told you this point, but this mechanism is still used for simple embedded system where we are pretty aware of all possible cases, all possible code that possibly executed while disabling the interrupt. And if there is no operating system layer provided for such a small system, this way, disabling the interrupt provide a quick way to make mutual exclusion in a very naive way. So still in embedded programming, this mechanism is used time to time. For a complicated program or complicated system, this approach is rarely used. Yeah, there are more reasons not to use this mechanism. So let me continue on. Reduce the concurrency. Reduce concurrency here means that if we design, even if there is no problem, I mean, if there is no code, buggy code or blocking code that is executed after the log operation, still this mechanism is not to be used because this reduces the chance of the concurrency. What's the big difference from this approach and this approach? You see here that log operation is parameterized with log variable. So even a log operation is executed and acquired a log, that effect is limited to the code that also execute the log operation on the same parameter log variable. So log operation in this form does not globally enforce atomic execution, but the atomicity is a guarantee upon the code that share the same log variable. However, if it happens in this way, you see that atomic execution, sequential execution is enforced globally in a system level. So no other code can be executed at the same time if a certain code is executed on critical section after this type of the log operation. So this is not a good idea. A third reason is that, yeah, it doesn't work on multi-core, multi-processor architecture. Why? In multi-core architecture, timer, beside the timer interrupt, it have a natural physical parallelism. So maybe two different logic is executing on two different cores. In such a cases, no matter timer interrupt is disabled or not, there is other code possibly executed on the other core so that disabling the interrupt does not help enforce atomic execution in multi-processor architecture. Last one, even if there is no problem for the three reasons above, still this mechanism is not favorable because disabling the interrupt is a very costly instruction. So it's not efficient at all. So this should be one theoretic possible implementation, but this is a very far from practical solution. Make sense? Have any questions so far, by the way? If you have a question, just open up your microphone and speak up.
Professor, just to clarify.
Sure.
The reason why this method is so slow is because it's like one stream. Am I understanding correctly?
That is the reason for the second one. I mean, that is what I refer to as a reducing concurrency. But the last one, inefficient here, means that instruction for disabling the interrupt instruction itself is a pretty slow instruction. Yeah, that's another reason.
Thank you.
Okay, good question. Have more questions? Okay, good. Then let me move on.